What specific problem does the proposed text-aligned tokenizer, TATOC, aim to solve in the context of unifying visual understanding and generation?
The proposed text-aligned tokenizer, TATOC, aims to solve the problem of unifying visual understanding and generation by creating a shared discrete representation that aligns visual tokens with the latent space of a large language model, LLM. This approach addresses the limitations of existing methods that often rely on separate representations for understanding and generation, which can hinder unified reasoning and complicate tasks like interleaved generation. By utilizing a text-aligned codebook initialized from an LLM's vocabulary, TATOC ensures that visual tokens are semantically aligned with textual tokens, facilitating seamless cross-modal input and output. Additionally, TATOC incorporates scale-adaptive pooling to control the granularity of visual details based on task requirements, enhancing both understanding and generation capabilities. Overall, TATOC simplifies the modeling paradigm and improves scalability by operating within a more efficient shared space.
How does the proposed method, particularly the TATOC, work? Please illustrate the step-by-step process of how images are converted into discrete tokens using the TATOC and how these tokens interact within the framework.
The proposed method, TATOC, converts images into discrete tokens through a systematic process. First, an image, I, is encoded into a continuous vector, Z_I, using a visual encoder, E. Next, this continuous representation is quantized into discrete tokens, Z_Q, by mapping it to the closest vector in a pre-initialized text-aligned codebook, C, which is derived from the token embeddings of a pre-trained LLM. The quantization is formulated as Z_Q equals text argmin _C in C, Z_IC squared. The codebook is designed to ensure that visual tokens are semantically aligned with textual tokens, facilitating a unified representation across modalities. Finally, these discrete tokens, Z_Q, can be utilized within the framework for various tasks, such as visual understanding and generation, allowing seamless interaction between the visual and language components of the model.
Can you provide a simple example to illustrate the inner workings of the TATOC? Walk us through the steps taken to convert an image into discrete tokens and how these tokens are utilized for both understanding and generation tasks.
The text-aligned tokenizer, TATOC, converts an image into discrete tokens through a series of steps. First, an image is encoded into a continuous vector representation using a visual encoder, denoted as Z_I equals EI. This continuous representation is then quantized by mapping it to the closest vector in a pre-initialized text-aligned codebook, C, which is derived from the embeddings of a pre-trained LLM. The quantization process is mathematically expressed as Z_Q equals text argmin _C in C, Z_IC squared, resulting in discrete tokens, Z_Q, that are semantically aligned with textual tokens. These discrete tokens are utilized in understanding tasks by feeding them into the LLM, alongside text prompts to generate outputs like captions or answers to visual questions. For generation tasks, the tokens can be autoregressively sampled to create a sequence of visual tokens, which are then decoded into high-quality images using either an autoregressive or diffusion-based detokenizer, allowing for seamless integration of visual understanding and generation within a unified framework.
What are the theoretical and practical benefits of employing a shared discrete representation in TATOC compared to traditional methods like VQVAE or separate encoders for understanding and generation?
Theoretical benefits of employing a shared, discrete representation in TATOC include the facilitation of unified reasoning across visual understanding and generation tasks, as both modalities are learned within a single latent space. This contrasts with traditional methods like VQVAE or separate encoders, which often lead to conflicts between understanding and generation due to their reliance on distinct representations. Practically, TATOC simplifies the modeling paradigm, improving scalability and reducing complexity by operating in a more efficient space, which is particularly advantageous for tasks requiring interleave generation or multi-turn editing. Additionally, the shared representation minimizes quantization errors through a scale-adaptive approach, enhancing the model's ability to generate high-quality images while maintaining semantic alignment with textual tokens. Overall, TA-Talk's design allows for seamless cross-modal input and output, significantly boosting performance in both visual understanding and generation tasks.
Explain the experimental design used to validate the effectiveness of TA-Talk. What datasets were utilized, what metrics were chosen for performance evaluation, and how did these contribute to demonstrating the method's efficacy?
The experimental design to validate the effectiveness of TA-Talk involved a comprehensive approach utilizing various datasets and performance metrics. The training data comprised 23 million high-quality text-image pairs curated from diverse sources, including image captioning and synthetic image generation, ensuring a robust dataset for both visual understanding and generation tasks. Performance evaluation was conducted using benchmarks such as GenEval and DPG Bench, where TA-Talk demonstrated strong results, achieving scores of 0.76 over 0.84 on GenEval and 82.96 on DPG Bench, surpassing other unified models. Additionally, ablation experiments were performed to assess the impact of key design choices, such as the text-aligned codebook and scale-adaptive pooling, which showed that these innovations significantly improved performance in both understanding and generation tasks. This multifaceted evaluation approach effectively demonstrated TA-Talk's efficacy in unifying visual understanding and generation within a single multimodal framework.
What specific results were reported in the paper that highlight the performance improvements achieved by TA-Talk over other visual representation methods, and what insights can you draw from these results regarding the method's capabilities?
The paper reports that TA-Talk outperforms other visual representation methods in both visual understanding and generation tasks. Specifically, the TA-Talk model achieves strong performance on the GenEval and DPG Bench, with scores of 0.76 over 0.84 and 82.96 respectively, surpassing all unified models and approaching the performance of state-of-the-art models like Janus Pro. In visual understanding, TA-Talk's 1.5B model surpasses most understanding-only models and matches the performance of Janus Pro 7B, which utilizes continuous visual tokens. Additionally, TA-Talk demonstrates high fidelity in image generation, outperforming pixel-based models that struggle with detail recovery. These results indicate that TA-Talk's shared discrete representation effectively balances the needs of visual understanding and generation, enabling superior multimodal reasoning and performance across tasks.